For these set of notes, we are going to talk about the VSEPR theory and bond polarity. VSEPR stands for valence shell electron pair repulsion. This helps us determine the shape of which the molecules will take on. And what it says is that the orbitals try to spread it apart as much as possible, because you got to remember that the electrons are in the orbitals and the electrons are negatively charged. And a negatively charged particle is going to repel another negatively charged particle. So that's why these orbitals are going to spread apart as much as possible at the greatest degree of angle to get as far apart, in which will cause the molecules to take on different shapes, which we will learn. There are some criteria that will help you to determine the shape of the molecules. So the first thing we're going to look at is when you have four things that are coming off that central atom. So here are three examples. So if all four orbitals, because there's four spots that these electrons can take, kind of we think of it as above the central atom, below, and to the left and to the right of it, but that kind of only goes for those structural drawings. But if there are four things coming off the central atom, there's no lone pairs, zero lone pairs. The angle which the four external atoms will take on between each of them will be a 109.5 degree angle, because again, that's the greatest amount of distance that they can get away from each other. So when we have four things coming off the central atom with no lone pairs, it's going to take on a tetrahedral shape. Tetra meaning four. That's probably the most easy, I think, for a lot of people to identify. An example would be methane, CH4. If we drew out the structural formula for that, it would look like this. The next example is when we have, again, it's still four things coming off the central atom, but there's going to be one lone pairs. And in this example over here, we're not seeing that lone pair of electrons. If I draw out the structural formula, it would look like this. So this ammonia NH3 is an example. So we would have nitrogen as my central atom. We have a lone pair of electrons up here. And then again, it's going to be that 109.5 degree angle coming off of it. And then we have our hydrogens. So there's still four things coming off that central atom. 1, 2, 3, 4, but one of them is a lone pair. And a lot of times we like to draw, don't have to, but again, those pair of electrons are taking on a kind of some space. So again, between each of these electrons is 109.5 degrees, as far apart as possible. And then the last example is, and that's called pyramid. A lot of times I will label it as trigonal, pyramidal. And then this last example is labeled as bent. So there's still, like I said, four things coming off that central atom, but two of them are being a lone pair. An example here is water. So if we drew in those lone pairs would be occupied up here. If I drew in as a structural formula, we'd have oxygen, our hydrogens coming off of here, and then those two lone pairs up top. And again, they also occupy space. And again, if we think about going back to whether or not molecules are polar or nonpolar, we would say that this molecule would be nonpolar because it has four external atoms that are the same. They have the same electronegativity. The poles on that central atom are going to be the same. For ammonia NH3, since it has this lone pair of electrons up top, this would automatically be a polar molecule. And then same thing down here for water. We've got lone pairs of electrons on that central atom, so this would also be a polar molecule. Thinking about the types of intermolecular attractions, this would just have a dispersion, intermolecular attraction. This would have dispersion and dipole-dipole, and same thing here would be dispersion and dipole-dipole. So 4 things coming off the central atoms. There's 3 different things that molecule could be based on: no lone pairs, 1 lone pairs, or 2 lone pairs. In this example, we have 3 things coming off the central atom. So here we have the first example would be trigonal planar or trigonal planar, however you want to say that. And this one has 0 lone pairs. So if I draw out the structural formula, it would look like this. Boron would be my central atom, and then I would have hydrogen coming off as the external atoms. And again, each line represents a pair of electrons that are being shared. They're going to try to get as far apart as possible, and resulting in a 120-degree angle all the way around that molecule. And then the next example would be if we had, let me erase this really quickly down here. Oops. Would be if we had 1 lone pair of electrons on our central atom. So sulfur dioxide is an example of this. We label this as being bent. We saw bent on the previous slide where there was 4 things coming off on the central atom, but here we're only having 3 things come off the central atom. So there's 2 examples where you will have bent as the molecular shape. Drawing it, it would look like this. We'd have sulfur. We've had 1 lone pair of electrons, just like how it says over here, and then we would have our oxygen coming off to the side. And again, that pair of electrons were going to take on some space. And again, between each of those electrons results in a 120-degree angle to try to get as far apart as possible. So we had tetrahedral on the previous slide, trigonal pyramidal on the previous slide, and bent on the previous slide. 4 things coming off the central atom. Now we have 3 things coming off the central atom, where we have trigonal planar and also bent. Looking at whether the molecule is polar or nonpolar, this would be a nonpolar molecule, so it would only have dispersion intermolecular attractions. And then this one, we have a lone pair of electrons on that central atom, so this makes this molecule automatically polar. So we would have dispersion forces and dipole-dipole. If there are 2 things that come off the central atom, it is automatically linear. And you drew it out. Carbon dioxide is an example of this. We'd have carbon as your central atom, and then we would have our oxygens coming off, and then between those there would be a 180-degree angle. Again, we will learn about how to draw these in future notes. So here we would have a linear shaped molecule. Again, looking at whether the molecule is polar or nonpolar, the external atoms are the same, so they have the same electronegativity. The pull on that central atom for those electrons are the same all the way around. So this would be a nonpolar molecule, only having dispersion intermolecular forces. Here's a chart that kind of shows you all the different examples. There's more than the examples that we've talked about. Like you can see down here, there are some things that we haven't talked about. So there's more examples of molecular shapes that we're not going to get into. But again, it tells you the shape, whether it has 0 lone pairs, 1 lone pair, 2, 3, 4. So we talked about the linear. We talked about the trigonal planar. We talked about the bent. And again, these are the number of things coming off the central atom. 4 things coming off the central atom. These are the 3 things that we talked about, and then we did not get into 5 or 6 things coming off the central atom. We just did these first 3. So take a second, pause the video, and see if you can determine the molecular shapes of these 5 examples. All right, here we go. So the pink being the central atom, we have 2 things coming off the central atom in this first example, so that makes it automatically linear. And this second example, we have a 120-degree angle, 3 things coming off that central atom. So that would be trigonal planar. Here we have 4 things coming off the central atom. So again, it takes on that with no lone pairs. So that's tetrahedral. Here we have, again, looking, these 2 things look like they're bent down. We don't know if there's 1 lone pairs or 2 lone pairs, but again, thinking about what this looks to me like water, just because I know what water is, but these 2 things are bent down. So this is bent. And without knowing what the central atom and the external atoms are, again, we won't know if there's 1 or 2 lone pairs, but it doesn't really matter about that right now. And then here we have 3 things coming off of that central atom. It looks different than this example. So I'm assuming that there's a pair of lone pairs electrons up top. So this will be, assuming that, again, there's a pair of lone pairs of electrons because it doesn't look like the trigonoplanar. So that would be 4 things coming off the central atom. So this would be, let me change the font color there. Trigonal pyramidal. Again, if you would, pause the video, and here you have the molecular formula and the molecular shape, and determine if the molecules are polar or nonpolar. All right, so for the first example here, we have a diatomic molecule, and they're the same. Again, there's not 2 things coming off a central atom, but there is no central atom. So this is automatically a linear shaped molecule. So we'll list the shape of that molecule, and then we'll also list the polarity. And since they're the same, this is a nonpolar molecule. And again, if we want to think about the intermolecular forces or intermolecular attractions, this would only have dispersion forces. This next example, NH3, we've seen this in a lot of the previous slides. So this is ammonia, that's the common name of this. You can see there are 4 things coming off that central atom, 1, 2, 3, 4, 1 being a lone pair of electrons. And so the shape will be trigonal pyramidal. That lone pair of electrons automatically makes this a polar molecule. So here we would have dispersion forces and then also dipole-dipole. So this, thinking about the stickiness of the molecules, if we're comparing ammonia to H2, this one would be stickier because it has more intermolecular attractions. And then this last example, CH4, this is methane. There are 4 things coming off the central atom, 0 lone pairs. So this would be a tetrahedral shape. This would be a nonpolar molecule because those external atoms are all the same. There's 4 hydrogens, so there would only be dispersion forces. So again, if we're talking about the stickiness of the molecule, this one would be the stickiness. And then comparing these 2, again, these are both nonpolar molecules. If they're both nonpolar, you'd have to look at the mass. So this one is larger, has more mass, so each hydrogen is 1, so this would have a mass of around 2, and then this would have a mass of 16. So this one is more massive, so this would be stickier than H2. So now we're going to get into talking about bond polarity versus just molecular polarity. So in the first set of notes, we introduced to you the two intermolecular attractions, the dispersion forces and the dipole-dipole. And I told you that there was a third type, and that third type is hydrogen bonding. Hydrogen bonding is a very strong dipole in which hydrogen is bonded to 3 specific elements: fluorine, oxygen, nitrogen. I like to remember as FON. Hydrogen bonding is not fun, but FON. So we have to look for first if there's any hydrogen in your molecule, and then we have to look, is hydrogen bonded to any fluorine, oxygen, or nitrogen? So for example, if we look at HCN, there is a hydrogen bonding happens, but it's only happening between the molecules, not within the molecule itself. So if we drew out that molecule, okay, we would have carbon as my central atom, would have a triple bond with the nitrogen and a single bond with the hydrogen. Again, thinking about the pull of those electrons, nitrogen is more electronegative than carbon, and carbon is more electronegative than hydrogen. So this would be slightly positive N, and this would be the slightly negative N. So when we have a neighboring molecule, we would have, again, a hydrogen here, carbon. So this slightly positive end would be facing that, and we'd have this intermolecular attraction going on between this nitrogen right here. That would be the intermolecular attraction. So we would have a hydrogen that is being attracted to a nitrogen. And again, this is an intermolecular attraction, not inter. So again, this is when it happens between molecules, between the neighboring molecules. Moving on, it says nitrogen, oxygen, and fluorine. They have a high electronegativity, so they pull hydrogen's electrons away from it, leaving its proton exposed. So again, why hydrogen bonding is specific is because these three have very high electronegativity values. If you look on that electronegativity chart, it is the strongest of the three intermolecular attractions, but it's going to be weaker than the covalent bonding that's happening within the molecule itself. So if we look at here at this water example, H2O, okay, so we have a hydrogen, and these dotted lines between our neighboring, we have a hydrogen that's being attracted to an oxygen. So since that, we would have hydrogen bonding going on, and so within this, if I drew out water, which is up here, oxygen has a lone pair of electrons. So it looks like this. So not only within these molecules, we'd automatically have dispersion forces. This molecule, water molecule, is polar because of the lone pair of electrons on the central atom. So we would have dispersion forces, dipole, and we can see the hydrogen bonding that's going on between the hydrogen and the oxygen in neighboring water molecules. So this would have all three types of intermolecular attractions, making it very, very sticky. This is just showing you the electronegativity values. This chart is also in the notes folder, which has a little sheet that you can print out if you'd like, or just you can always access it in that notes folder. So if you think back to when we talked about periodic trends, we said that the electronegativity value tends to rise as you move towards the northeast top right corner of the periodic table, and those electronegativity values decrease as you move southwest. So again, we're talking about polar, and they're using a polar bear kind of as an example. Here's a compass. So again, the top right corner, northeast corner, those values have very high electronegativity values, high tendency to attract electrons toward themselves. And then you see these ones are large polar bears. And then down over here, we have small little penguins. Down here, these have very low electronegativity values. So up until now, we've been talking about whether the molecule itself is polar or nonpolar. We can also look at the bonds, what's going on within the molecule itself. So most bonds are a blend of ionic and covalent characteristics. The difference in electronegativity will determine if the bond between two adjacent atoms are going to be ionic or covalent, or possibly we know there's a third type, metallic, but we're not really going to be talking about that in this example. Ionic bonds are stronger than polar bonds, and polar bonds are stronger than nonpolar. Ionic is stronger than covalent, but covalent is also stronger than those polar bonds. So again, if we look at this diagram over here, this is going to tell you whether the bond itself, not the molecule, the bond is going to be ionic, polar covalent, or nonpolar covalent. So again, you'd have to look on your electronegativity chart, and you're going to do the difference of those electronegativity values and see where it falls within this range. So if you have two electronegativity values and you subtract them from each other and they fall within this range, then that bond between those atoms would be ionic. If you did it and it fell within this range, it would be polar covalent, and then 0 to 0.3-ish it would just be a non-polar covalent bond. So again, we're looking at those electronegativity values, subtracting them, and looking at where they fall within this range. So like I've been saying, electronegativity is an attraction an atom has for a shared pair of electrons. Again, ones that have a higher electronegativity value will pull those shared electrons slightly closer to that atom, causing it to have somewhat of a negative charge, and we note it with this sigma negative symbol. And then the ones that have a lower electronegativity value, those electrons are going to be pulled away from it, causing it to be slightly positive. So you can see in this example of HCl, hydrochloric acid, chlorine is more electronegative, so those two electrons that are being shared between hydrogen and chlorine, they're going to be pulled slightly closer to chlorine, making the chlorine end slightly more negative and the hydrogen end slightly positive. And thinking about when we talk about ionic size, that's why this end is slightly larger, because again, when you had negative ions, that ionic size of that ion got larger, cations became smaller. So I just kind of explained this example on the previous slide for the HCl, hydrochloric acid. It says bonded pair of electrons spend more time near the chlorine's nucleus because chlorine is more electronegative than hydrogen. Looking down here at my polar bear example, again, chlorine is more electronegative. It has a higher electronegativity value, so again, our polar bear is larger. And the ice cream, again, we have two scoops representing the two electrons that are being shared between the penguin and the polar bear, and the polar bear is pulling those electrons, in this case the hydrogen or the ice cream, closer to that, making this end slightly negative. So looking more specifically at the bond type, whether it is polar, not polar covalent, or nonpolar covalent, here for a nonpolar covalent bond, the electrons are shared equally. It is symmetrical in electron density, and usually this is for identical atoms. So like mainly the H7 are 7 diatomic molecules. They're both going to have the same electronegativity values, so that's why we say the electron density is symmetrical. It's the same, and one end is not larger than the other end, like we saw with the hydrochloric acid example. You can just see it's just a nice round oval, meaning the electrons are being shared equally between the two. Just another example of nonpolar covalent bonds. We have two polar bears. Again, they have equal strength. Two penguins, equal strength. Here we would have nonpolar covalent bonding occurring. If we have a polar covalent bond, that means the electrons are being shared unequally. One end has a higher electronegativity value, making one end slightly negative, one end slightly positive. It's asymmetrical in the electron density because, again, the one that has a higher electronegativity value will pull those shared paired electrons closer towards itself, and this will result in a partial dipole charge. So again, these two atoms will both be nonmetals, again, covalent bond, but that bond between those two atoms are going to be polar due to the difference of electronegativities. This is again another example of a polar covalent bonds. Again, the pair of electrons are going to share more time toward the nucleus of the more electronegative atom. The other atom has a partial positive charge. Again, thinking about our HCl example, again, the polar bear is pulling the ice cream closer to itself, making it slightly negative, and this end slightly positive. So if the electronegativity values of the two bonded atoms is unequal, then their bond will be polarized, maybe a little, maybe a lot. And in this case, this is where we can get an ionic bond forming between the atoms, and in that case, we know it's those electronegativity values have the biggest difference, and when we have a very large electronegativity difference, it usually happens between a metal and a non-metal. So this is kind of just showing you the shape of the electron cloud for the type of bond that we have. So again, we have nonpolar covalent bonds happening between two usually identical atoms. They have the same electronegativity difference. So again, nice round oval, the electron density is the same. Here we have a polar covalent bond, non-metal, but one end has a slightly higher electronegativity value, pulling those shared pairs of electrons closer to one end, making one end slightly negative, one end slightly positive. And then if we have a very large electronegativity difference, one atom will turn into an ion, taking away an electron or electrons, and making one negatively charged our anion and one positively charged our cation. This is again just showing you an example using the polar bear and the penguins. Again, two identical, sharing them equally. Again, if we have hydrogen, oxygen, oxygen, hydrogen, hydrogen, again, electron cloud showing the electron density. Polar covalent, again, HF, hydrofluoric acid. This end will be slightly negative, this end will be slightly positive, and a very large electronegativity difference where this is taking the electrons away and he's taking the ice cream away, making, now we have ions, cations and anions. So you've been seeing me draw arrows to show which way the electrons are being pulled toward one side or the other. I do need to make a correction. I've been saying that this is the Greek symbol sigma, but I completely slipped my mind. It's actually the Greek letter delta. Again, it's just a symbol that we show which end is slightly negative, slightly positive. Apologize for that little mishap. Again, we just use these symbols to show which end is more slightly negative, slightly positive, and the arrow, whether you draw it down below like here, or you can just actually draw it on kind of the bond to show the direction in which those electrons are being pulled. So in general, a bond is polar if the difference in electronegativity between bonded atoms is 0.3 or more. So again, these, you saw this, now I'm just kind of giving you a range, 0 to 0.35, nonpolar covalent, 0.36 to 1.7. We have polar covalent, and anything greater than 1.7, that's where we will have ionic bonding. So if you look at carbon and hydrogen's electronegativity difference, if you subtract them, they are going to fall within this range, making this bond between the two nonpolar covalent. Here are a couple examples. So we have chlorine and chlorine. Obviously, they are identical atoms. They have the same electronegativity. So if you look on that chart, they're both 3.16. So if you subtract the two from each other, the value is 0. So again, that's going to fall within this nonpolar covalent range. Looking at hydrogen and chlorine, we have chlorine's electronegativity as being 3.16, hydrogen's electronegativity 2.2. Subtracting the two, it comes out to be 0.96. Looking within this range, it falls polar covalent. So again, we have between the hydrogen and chlorine, that's going to be a polar covalent bond. And then looking at sodium chloride, chlorine has an electronegativity of 3.16. Sodium's electronegativity is 0.93. Subtracting the two, the difference comes out to be 2.23. Looking at it, it is greater than 1.7. So the bond between sodium and chloride is going to be an ionic bond. And like I mentioned before, this is all about the bond between them, not the molecule or the compound itself, just what's happening with the bond between the two. Here are a couple more examples. So if we have nitrogen trichloride, if we see nitrogen here as our central atom, and then these three green are the chlorine. So I look on the chart over here, nitrogen's electronegativity is 3.04. Chlorine is 3.16, a difference of 0.12. So I look on my scale here, and that falls within this range. So the bonds between the nitrogen and the chlorine are going to be nonpolar. Again, this is going to talk about what's happening with the bond, not the molecule itself. So here we have nonpolar bonds happening, but this molecule itself is polar because what we don't see here is that there are one pair of lone electrons up top. So this would be trigonal pyramidal shape. So the bonds are nonpolar, but the molecule itself is polar. same thing can happen. You could have polar bonds, but again, the whole molecule itself could be nonpolar due to the electronegativity, the difference in electronegativity being the same all the way around that central atom. Looking at this next example, we have two central atoms, both of being the carbons. These gray on the outer are hydrogens. Looking at the electron, carbon 2.55, hydrogen 2.20, a difference of 0.35. Looking at that range, here we would have nonpolar. So this would also, so we have nonpolar bonds between the carbon and the hydrogens, and then also the external atoms are all the same. So this would be this would have nonpolar bonds and a nonpolar molecule. Here we have water. Water also has these two pairs of lone electrons up top like that. So I look at the electronegativity values. Oxygen 3.44, hydrogen 2.20, a difference of 1.24. It falls within this polar range, so we would have polar bonds, and because of these lone pair of electrons, it makes the molecule itself polar also. Okay, let me write these in. Okay, so we would have nonpolar bonds, nonpolar molecule. And again, if we think about the intermolecular attractions, this would just have dispersion forces. For water, we said it had polar bonds. It's a polar molecule. And we would have dispersion forces. Because it's polar, it would have dipole-dipole, and we have a hydrogen in our molecule, and that hydrogen will be attracted to the oxygen in a opposite neighboring molecule, so we also will have hydrogen bonding going on too. And our last example down here, we have carbon as our central atom. We have hydrogens, we have fluorines down here. So here we are going to have two different types of bonds. So with our fluorine, we have 3.98, and then to our carbon, 2.25. So a difference of 1.43, and then also our carbon to hydrogen, a difference of 0.35. So this is our carbon to hydrogen, our carbon to fluorine. So this is going to be nonpolar bond between the carbon and hydrogen, but the bond between carbon and fluorine fall within that polar range. And because the electronegative poles are not the same all the way around, if these are hydrogen, carbon is going to pull those shared pair electrons closer to itself, and the fluorine will also pull those closer to itself. So we also have a polar molecule, and we are going to have dispersion forces, dipole-dipole attractions, and then if you can see, if this is a hydrogen, it can face a fluorine in a neighboring molecule, which we can also have hydrogen bonding going on. So if the bond itself falls within that polar range, those polar bonds make dipoles. And dipoles can refer to a couple different things. It can refer to the polarity of an individual polar bond itself, the net polarity of a polar molecule that may consist of several covalent bonds, or the polar molecule itself. So again, we can kind of show that by using our symbols, our delta symbols, showing that one end is slightly positive, one end is slightly negative, showing you the arrow in which the electrons are being slightly pulled closer, and that kind of references the dipoles. So we've been mainly just been talking about bond polarity, but I'm saying don't forget about molecular polarity. So they're kind of different. So molecular polarity is different than bond polarity. Nonpolar molecules, like I said, can have polar bonds, and polar molecules can contain nonpolar bonds. But again, thinking about how those electrons are being pulled all the way around that central atom, if it's the same, then that's where we can have polar bonds but a nonpolar molecule, and vice versa. A molecule that has all nonpolar bonds is automatically a nonpolar molecule. And an example of that are hydrocarbons. They have carbons and then hydrogens attached to all of those. So the carbon to hydrogen bonds are nonpolar. If you look at the electronegativity differences, it's going to fall within that nonpolar range. And since all of them are the exact same, we have nonpolar all the way around, it makes our molecule itself automatically nonpolar. And then if you think about the intermolecular attractions, it would only have dispersion forces. So this slide references how you can have polar bonds, but the molecule itself be nonpolar. So the polar bonds in a molecule can cancel out if the central atom has no lone pairs and all the bonds are the same. So our examples of this would be linear, tetrahedral, and trigonal planar. So if you look at this example down here, we have our central atom. Our central atom is showing it's slightly positive, so it must have a lower electronegativity. These external atoms must be the same. They're the same color, the same size, so I'm thinking that they have to be the same atoms, and they have a slightly negative charge. I'm telling you here that this is a polar bond, so those difference in electronegativities fall within that polar range. But again, this pull upward is going to get canceled out with this slightly downward pull on this left atom combined with the slight down pull of this right atom. So these two slightly down and to the left and down to the right will cancel out that one that's being pulled up. And then this slight down leftward pull will cancel out with this slight down rightward pull. So the pull all the way around they get canceled out. And this is where we can have polar bonds, but overall a nonpolar molecule because those polar bonds, like mentioned up here, can cancel out on that central atom. So for this last slide, I'm going to mention it only because some of you guys might Google some information. So there's a little gray area. So on a couple slides back, we had mentioned that if the molecule contains all nonpolar bonds, the molecule itself is automatically nonpolar. If you by chance look at nitrogen trichloride or phosphorus trihydride, they're only very slightly polar, and you might find that some websites will call it nonpolar because they're comprised of all nonpolar bonds. But like we said before, due to these lone pair of electrons on the central atom in both of these examples, going along with what we've talked about in class, we would characterize even these bonds are going to be nonpolar. This lone pair of electrons makes this overall molecule polar. So just go off of what we've learned and talked about in the notes that we just covered. If there is a lone pair of electrons on that central atom, we'll just say the molecule itself is polar, even though all the bonds would fall within that nonpolar range.